In section 5.3.4, we will discuss the comparison between electrostatics and magnetostatics. So we will not go towards the dynamics, but only to the electrostatics of the two, as we have discussed in the second chapter, the electrostatics portion, and in the fifth chapter, we started with the magnetostatic portion. So as we are done with the electrostatics and magnetostatics, so let's discuss different aspects of the two. So here we are having, first we discuss the electrostatic situation. In electrostatics, we know the first one is the Gauss's law, which is the divergence of electric field is equal to the charge density, the volume charge density rho over epsilon naught. Like when there is a source, there is a charge, then the electric field lines will diverge from the charge distribution. And we say in the electrostatics that del cross E, the electric field lines are not curling at all. They are diverging, so divergence means going in a straight line, and they are not curling. We can write this in, this is like Faraday's law for electrostatics and Gauss's law. We can write them in integral form, and this is on a closed surface, and E dot dA is equal to Q enclosed over epsilon naught. Similarly, this one in integral form we have already written that this is our closed path, and E dot dl means the path integral is equal to 0. Around a closed loop, the path integral is equal to 0. We call this a conservative field. Del cross equal to 0, a conservative field. Like the field lines are not curling. So moving from one point to another point, we will have to do some work against the electric field. But if we do that work around a closed path, means the point from where we start and we reach back that point, then the work done will be equal to 0. This is the same thing, E dot dl is equal to 0. So we call it a conservative field. Similarly, when we are here, so let's discuss a little bit magnetostatics, and then we will do more comparison. Here is when there is a source, then there will be a diverging electric field. Electric field will be diverging from this. And when we are in magnetostatics, in magnetostatics, we know that the source is not charge, but current. Although current is the moving charge, but we call, for the sake of, you can say, magnetostatics, like it's having a source, a steady current. So magnetostatics, and we have just in resemblance to that one, that del cross B equals mu naught G. Mu naught times means the current magnetic field. When there is a current density, when there is a current, there will be a curling magnetic field. And it's a source here. Similarly, when the magnetic field lines are curling, then it means the magnetic field lines are not diverging. del dot B equal to 0. And we can write their integral forms. So this comes out to be closed path integral, and it will be B dot dl equals mu naught I, and this is enclosed, and this will be del dot D equal to 0, so we will have here that B dot dA is equal to 0. B dot dA is the magnetic flux. When the lines are not diverging, then they are definitely curling, and the curling lines are having their flux equal to 0. So this is when we are having a source here, so the electric field lines are diverging from it. So the electric field lines are basically starting from one point and ending at the other point. Like starting from a positive charge, then they will be ending at infinity. But if we are having a dipole situation like plus and minus charges, then it will start from the plus and ending on minus. When we consider the field lines of this, then if for example we are having source and source like a positive charge, then the field lines are diverging from this. This is just a geometrical representation. These lines are not real, but the vectors are basically showing the diverging electric field. These are the representation lines with us. Similarly, if we are having a long wire, a current carrying long wire, and let's say this is going out of the board, so we have the magnetic field lines just like going around this. So the field lines, they are continuous line. They are not starting from a point and not ending at a point. They are continuous lines. We call this a solenoidal field. The electrostatic case, we call it the conservative field, and we call the magnetic situation is a solenoidal field. So these are the magnetic lines. We have one thing which is common between the two is the electric field goes to 0 at infinity. When we are far away from the source, the electric field lines, the electric field will go to 0. Its strength decreases, is 1 over r squared. These lines are falling quickly. When we go to the magnetic field, then the magnetic field is going to 0 at infinity. So this is the same situation, but the magnetic field is going to 0 slowly compared to the electric field, because that is 1 over r as we have already derived. Then we can have in the electrostatics, when we are having two charges and they are interacting with each other, so we are using the Coulomb's law of interaction, and for many charges we go towards Gauss's law. And in the case of magnetostatics, we are having for the line, and if we are finding the magnetic field around it, then we are having the equivalent of Coulomb's law is our two current carrying wires interacting with each other like two charges there. So we are having Biot-Savart law, and for many we can apply the equivalent of Gauss's law is Ampere's law. So this is both of them are actually following the superposition principle. If many charges, so we will have to apply the superposition principle. Similarly, many current sources, we will apply the superposition principle here as well. So this is one of the mathematical equivalence between the two here. The other thing that says similarities, or you can say the comparison between the two. This one says that this electric monopole exists. When its divergence is non-zero, then it means the electric monopole or a single charge exists for this field. And when we say that the divergence of magnetic field is zero, it means that magnetic monopole doesn't exist, because if it would have been existing, then the divergence would be non-equal to zero. So magnetic monopole doesn't exist. And the other thing is that the electrostatic field is going in a straight line, while the magnetic field is rotational, means around the source. Although the magnetic monopole doesn't exist, there are some theories which predicts the existence of magnetic monopole, and in high energy physics or in particle physics, we are having some theories that basically predicts the existence of this, but we don't have any experimental verification for this thing. Now, in most theories of physics, they are working when we say that magnetic monopole doesn't exist. So this is the one of the comparison here, and let me compare it even more, like the relative strength of the two. So before going into the relative strength, let me discuss a little bit about the potential here. Now, when we say that del cross E is zero, for this one, magnetic fields are not curling. Their curling is zero. It means, not the magnetic, the electric field. The electric field lines are not curling. So it means the electric field is the result of something which is varying in a straight line, or which is based on something in a straight line, which we call the potential of this. So del cross E gives the indication that the electric field is the result of the straight line. So del for the gradient, and del is there, so it's a vector, and here a vector, so we have a scalar potential here and a negative sign due to the reference, because it is all reference whether we consider the work done by the electric field positive or negative. So it is just a reference point, and like the electric field work, if the electric field is doing it, we consider it positive. If we are doing work against the electric field, we consider it negative. So it's just a matter of reference. So electric field is the result of the negative gradient of potential, straight line. And now consider the same situation here, that when we say that the divergence of B is zero, it means that magnetic field lines are not diverging. It means B is the result of something which is curling, and I write its potential that B is basically equal to something curling, and this is del cross A. So in the case of magnetic field, we are having a vector potential, while in the case of electrostatics, we are having a scalar potential. So it's the difference between the two. The electric potential, in case electrostatics, we are having electric potential, and in magnetostatics, we are having the magnetic vector potential.